Hi students, now we are going to explain one type of motion which is called as rolling motion. Now what is a rolling motion? What is the best example for the rolling motion? For that I have taken a circular wheel. So in the circular wheel it is going to rotate about the center. That center through which the rod is passing is called as the axis of rotation. Now I have considered two particles only. One particle is exactly at the center of mass of the wheel, and the other particle I have taken on the rim, edge of the wheel, that is called as rim. So I will place this wheel on a flat surface like a track or a road. Now can you see the two particles? One at the center, which is called the center of mass. The other one is at the rim, that is edge of the wheel. Now you observe what happens to the position of the two particles when I rotate. Okay, now you observe I am rotating the wheel, okay, on the track. Can you see after 1/4 of a rotation, the particle at the center has not changed its position, while the particle at the rim has it changed its position or not? So this is after 1/4 of a rotation. Another 1/4 I will rotate. You see the position of the particle at the rim, where it is coming, you see, at the highest position. But still the particle which is at the center or the center of mass doesn't change its position. Okay, after another 1/4 of a rotation. So you can see the change in position of the particle at the rim. Now also the particle at the center is not changing the position. Now the last 1/4 of the rotation, when it is completed, the wheel has completed one full rotation. The wheel has completed one full rotation. So now the particle which started from the rim, it has come back to the original position after completing one rotation of the wheel. But the center of mass is still there only. But if you consider the initial point and the final point, now both the particles have completed the same distance, that is equal to the circumference of the circle. Okay, now you can look at the board. The same wheel is diagrammatically represented. So I take A is the initial position of the wheel. So one particle colored red colored particle, no, this is the particle on the rim, outer edge of the wheel is called the rim, and the blue colored particle is at the center of mass, and R is the radius of this wheel, the circular wheel's radius. So after 1/4 of the rotation, the particle at the rim has come to this position. After 1/2 rotation, this particle at the rim has come to the highest position. Then after 3/4 rotation, the position of the particle at the rim has changed, and finally after one complete rotation, the position of the particle at the rim is here at B. Okay, so how many rotations the wheel has now completed is one full rotation. So this one full revolution or the rotation distance traveled between A to B is 2 pi r. So this distance traveled by the particle at the rim is equal to at 2 pi r. At the same time, the particle at the center of mass also has come from this position A to this position B. It has not changed its position, that's all, but it has also moved with some velocity. Understand? With some definite velocity, it has moved from A to B. So that velocity with which the particle at the center is moving, that is called as velocity of the center of mass. And you see that the center of mass, the particle is moving along a straight line. So the motion exhibited by the particle at the center of mass is along a straight line, and hence it is called as the translatory motion. Okay, then the particle at the rim, this particle at the rim is rotating, is it not? So it is rotating about the center of mass. So it is having a rotational motion and also translatory motion. Now I will join the position of the particles at the rim. So you see here the particle at the rim is here. So when I join this particle here, then from here the position is joined. Then from this position I come here and then I come here. And what next is going to happen is the repetition of the same like this on both sides. So can you see that this is like an arch? Is it not? Like an arch of a bridge. So this is the graphical representation of the motion of the particles on the rim. One particle I have shown here. So like that the next particle on the rim followed by all the particles. All the particles on the rim will follow this type of path which is called as a cycloid. So the particles on the rim of the wheel, they follow what path means? It is a cycloid. Understood that? So it is a combination of translatory motion and rotational motion. Whereas the particles at the center of mass, they will follow a straight line path. So I can write now the velocity of a center of mass, okay, Vcm is also equal to V translatory. So what is the translational velocity of the particle at the center of mass? No, as well as all the particles, their translatory motion or the velocity due to translatory motion along a straight line will be the same, and hence it is also equal to the velocity of the center of mass. So my dear students, you must understand that rolling motion is a combination of translatory motion as well as rotational motion. So it is a combination of translatory motion and rotational motion. Which particle only is exempted from rotational motion is the particle at the center of mass. All other particles will have two types of motion, that is translatory motion and rotational motion. So as a combination of these two types of motion, what is the path followed by the particles except that at the center? That is a cycloid. Okay. Now let us find out the resultant velocity, because except the particles at the center, all other particles will be having two velocities. One is rotational velocity and the other one is translatory velocity, that is equal to the velocity of the center of mass. So the translatory velocity is nothing but the velocity with which the center of mass is moving. So Vcm is equal to V translatory. And what is V rotation? So due to this rotation, you see here in this picture I have shown the translatory velocity of all the particles. So all the particles on the rim as well as in between the rim and the center also there will be some particles. So their translatory velocity will be the same, because they will take the same time to travel a distance equal to 2 pi r. Is it not? When the wheel completes one full rotation, what is the distance traveled by all particles on the wheel, be it at the center or at the outer edge? They all must have completed a distance equal to the circumference of the wheel, that is equal to what? 2 pi r. Therefore, the translatory velocity of all the particles, whether they are at the center or at the rim or in between the rim and the center, all will have the same translatory velocity. So I have written here the particles are all having the same translatory velocity. So this is a translatory or translational. Okay, both are one and the same. Translational velocity. I am going to add this. Okay, I am going to add this with the rotational velocity by taking the particles at the rim. So this rotational velocity V rotation, okay, V rotation is equal to R omega, where omega is the angular velocity of the wheel. So what is the expression for the rotational velocity of the wheel? Radius times its angular velocity. So V rotation is equal to R omega. So when I add this translational velocity with the rotational velocity, then I get an expression for the resultant velocity. So here I am going to get the expression for what? The resultant, okay, resultant velocity. Now you look at the first picture, the direction as well as the magnitude of the translational velocity is shown here. Okay, if you want in vector form also you can represent so both in magnitude as well as direction. So like that here also V rotation. So V rotation is also expressed in vector form. It is tangential to the circular path. So for this particle, if you draw a tangent, means it will be towards the right, and for this particle it is downwards. This is to the left and this is upwards. Now the same particle you see here, the same particle is having translational velocity as well as rotational velocity. So in third picture I have represented these two velocities, okay, both simultaneously I have shown here. In the first picture I have represented only the translational velocity of all the particles. In the second picture I have shown the rotational velocity of all the particles on the rim except the center of mass. All are rotating. So in the third picture I have shown together. So what is the direction of the translational velocity? You see here, this is the translational velocity, this is rotational. Now this translation velocity is along the horizontal direction and rotational velocity in the vertically upward direction. So the angle between these two is what? 90 degree. Now how do you find the resultant of two perpendicular vectors? By completing a parallelogram and drawing the diagonal of the parallelogram. So you can look here, students, the V rotation is upwards and V translation is along the horizontal. So the resultant of these two is represented by V itself. V is the resultant of these two. So I can write the resultant velocity V vector is equal to V translatory vector plus V rotation vector at any point. Okay. So in this picture you can see for the particle which is on the left side of the rim, the resultant velocity direction is in between these two. Okay. This is the resultant velocity in magnitude as well as direction. Then at this position where the particle is at the highest position, you can see the direction of translatory velocity as well as the direction of rotational velocity, both are in the same direction. Is it not that? Like that, you look at the particle which is at the right side of the rim. So here direction of translatory velocity and the direction of rotational velocity I have projected here. Direction of translation velocity and rotational velocity. So you see the resultant velocity both in magnitude and direction. Similarly, at the point of contact, this is to be understood very carefully. When the wheel is coming in contact, you see the red color dot. When it is coming in contact, momentarily it is at rest. You have to understand very carefully. It is not permanently at rest, momentarily at rest. So when this particle at the rim is momentarily at rest, then you must see that the V translatory, okay, so this is a V translatory and V rotation, they are opposite directed. They are oppositely directed. Understand? So the resultant velocity must be 0, is it not? When it is momentarily at rest means naturally the resultant velocity must be equal to 0. Is it not? So the magnitude I will take, see here V rotation is on the left side and V translatory is on the right side. So this is equal to, that is a V rotation minus of V translation is equal to 0, or V rotation is also equal to V translatory and that is also equal to V CM. This is a very, very important information, my dear students. You have to remember forever. See, we have finally proved that with a simple equation that the magnitude of the rotational velocity and the magnitude of translational velocity both are one and the same. Okay, both are one and the same. So, at the bottom point, the resultant velocity is equal to 0. And rotation is on the left side, translatory motion is on the right side. So V rotation minus of V translation must be equal to 0, or V rotation equal to V translation is equal to V center of mass. Okay, by the same lines, you look at the point on the top. So on the top here, the resultant velocity must be equal to what? Okay, V translation. Okay, V translation plus V rotation. The magnitude, if you add, means it is VCM plus VCM, that is equal to what? Twice the velocity of the center of mass. Understand that? So at the highest point, the resultant velocity of the particle on the rim is equal to what? Twice the velocity of center of mass. At the bottom point of contact, since the resultant velocity is 0, the particles on the rim which are in contact with the surface, they are momentarily at rest. Okay, now so far we were discussing only about two particles, that is one at the center of mass and one at the rim. There may be other particles between these two are also not. They have how many types of motion? Two. One is translational, the other one is rotational. Now let us see one more point in between the blue and the red. You see one black color spot. For this particle, okay, it is at some distance small r. This particle, random particle I have taken, it is at a distance small r from the center of mass. So it is having two velocities. One is rotational velocity, that is tangential to the circle, and the other one is the translational velocity along this direction, horizontal. So what should be the resultant of these two velocities? Again, by parallelogram law, we can complete a parallelogram and the diagonal will give you the resultant. Is it not? So the resultant velocity V is shown red in color. And here you must know that this radius of this inner circle, the radius of the inner circle is perpendicular to V rotation. Perpendicular to V rotation, because V rotation is acting along a tangent. Tangent must be perpendicular to the radius. So keep in your mind the rotational velocity. The rotational velocity is always perpendicular to what? The radius of the circle on which the particle is located. Okay. Now, if this particle's position is joined with the point of contact, this is the point of contact. So, at this point of contact, okay, if you join, this will give you the position vector of the particle with respect to the point of contact. If you observe, means that will be perpendicular to the resultant velocity of the particle. Okay, that must be perpendicular to the resultant velocity of the particle. So, V rotation is perpendicular to the radius of the smaller circle, and V is perpendicular to the position vector of the particle. From which point? From the point of contact. So, here you must very well remember that rolling motion is a combination of translatory motion and rotational motion. So, except the particle at the center or the center of mass, all other particles will have two velocities. That is translational velocity, which is also equal to the velocity of the center of mass, and rotational velocity, which is equal to the radius times its angular velocity. So, different particles are at different radii from the center. So, their rotational speed okay, may be different at any point. The combination of rotational and translational velocity can be found by using parallelogram law. And at the point of contact, the particles which are touching the surface will be momentarily at rest. So I hope you must have understood the rolling motion. So all the automobiles, the two-wheelers and the four-wheelers and all are following this rule only. Okay, I hope you must have understood well. Fine.